Okay, now we're talking about inclined planes. Now, draw a free body diagram. We've done some before. Choose the object of interest and draw it as a small box. Draw and label all of the external forces. Label a coordinate system. And for an object on a ramp, it makes sense that the coordinate system would go up or down the ramp, and we'll see that in a minute. When forces don't line up with your axes, you're going to have to draw a pseudo free body diagram. Now, free body diagram again shows all the forces. Well, a pseudo free body diagram breaks the forces up that don't line up with the axes into parts that do line up with the axes, and it makes it much easier to solve. So you're going to redraw your diagram with all the forces perpendicular or parallel to the axis. This is purely designed to help solve the problem. It's not designed to practice your free body diagrams. It's useful in solving the problems. So if we have a box sitting on a ramp, that's what we're talking about. The key thing, it throws a few things out of kilter from what we thought before. The normal force is no longer equal to the weight because the weight is acting straight down towards the center of the earth, which we know. That's what gravity does. Gravity is a pulling force. The normal force is a perpendicular reaction force from the surface. Since those don't line up, they're no longer equal to each other. They're equal to each other on a flat surface. As soon as you involve a ramp, they're no longer equal to each other. Friction, we know, opposes motion. You're going to have to guess which way motion is going to occur. In this case, the box is going to want to slide down the ramp, so friction acts up the ramp like that. Now's where I tilt my coordinate system. I tilt my coordinate system in where I have an X and a Y. I got X and Y backwards. I'm going to line it up with the ramp. So therefore Fn is perpendicular to the ramp. Ff is in the direction of the ramp. Fg, though, is the oddball. So what I'm going to have to do now is use a little trig and make Fg where part of it goes with the ramp and part of it goes into the ramp. So the force down the plane is the part of Fg that points down the plane. You'll sometimes see that written as force parallel because it's parallel to the plane. I like force down. For me, that works. The other part is the force that's perpendicular to the plane. The force that's perpendicular to the plane causes the normal force. In other words, the box pushes into the ramp pushes back. The normal force is equal to the perpendicular force. Now, it also makes a lot of sense mathematically to redraw the force down at the opposite end of Fg. Now I have a right triangle. Now I can do a little trig. Fg is my hypotenuse. The force down is opposite of theta, and the force parallel is adjacent. Because of geometry, that theta has to equal the theta of your ramp. So sine of theta, well, sine of theta is opposite divided by hypotenuse, so it's FD divided by FG. So when I try and solve for FD, FD is going to equal FG times the sine of theta. And that's kind of important. That's going to give you the force down the plane. It's simply the weight of the object times the sine of the angle. Now, for cosine is adjacent over hypotenuse. So the adjacent side is the force perpendicular to it. So it's force perpendicular divided by Fg. When you solve for force perpendicular, you get force perpendicular is equal to Fg times the cosine of theta. The force perpendicular is the normal force. So it's equal. Now remember, the force perpendicular when an object's sitting on a flat surface, well, the cosine of 0 is 1. So therefore the equation still works. Excuse me. So when I redraw my pseudo free body diagram, now I can solve it. I have FF and the force down the plane lined up in that direction, and I have the perpendicular force and the normal force lined up. So now I can sum the forces in either one of those directions. The normal force and the perpendicular force are always going to add up to 0. You're not going to accelerate into the plane, but you will accelerate down the plane. So by playing with the force of friction and the force down and other forces that are added, I can then change it. So let's apply it to a problem. A box is at rest on a ramp as shown. The vectors are not drawn to scale. The net force is equal to what? Well, the key thing here, the word that should jump out to you is rest. Now, if that word jumps out to you, rest means the acceleration is 0. If the acceleration is 0, what's the net force? 0. A 5 kilogram box is at rest on a 30-degree inclined plane because of force F. Calculate the value of F. Now I'm telling you now it's at rest, and I want to calculate what force is needed to keep it at rest. Now they don't say me anything about the inclined plane, so I'm going to ignore friction in this case. Rest, though, is important. That tells me the forces add up to 0. So my free body diagram, I have force up the plane, I have Fg going down. I should also have a normal force perpendicular to the plane. I just missed it. Now my pseudo free body diagram, I have F acting up the plane, I have F down going down the plane, and I have F perpendicular and F normal. Again, that's my pseudo free body diagram. Now I'm only really worried about the X direction. So now what I'm going to say, and I'm going to say up is positive because F is positive. Now I have my Y component there. All that really tells me is the normal force is equal to the perpendicular force. So force normal equals force perpendicular. Now the sum of the forces in the X direction is what I'm worried about, and those have to add up to 0. Rest tells me something. Remember, rest and constant velocity are important. So therefore F minus F down has to equal 0. F down is negative because it's acting down. F is positive because it's acting up. So therefore F has to equal FD. Now we go back to what we talked about earlier. FD is mg times the sine of 30 degrees. Well, 5 kilograms, 5 times 10 is 50 newtons. 50 newtons times 0.5 is 25 newtons. So 25 newtons would hold it in place. Whoops, you can see the answer. For an object being pushed up a rough, which free body diagram is correct? Well, obviously you can see E is correct. You know the force applied is up. Fg acts straight down the plane. Fn acts out of the plane perpendicular to it. And since you're trying to push it up, friction is going to act in the opposite direction. All of the rest of them have either not enough vectors or not correct vectors, so E is the best answer. Diagram shows a 1 times 10 to the 5th Newton truck on an 8-degree incline. What is the component of the truck's weight parallel to the incline? What they're asking you for is the force down the ramp. Remember, weight acts straight down. So I'm looking for force down. Force down is my unknown. Force down is equal to mg times the sine of theta. Well, they gave us mg, 1 times 10 to the 5th newtons, times the sine of 8 degrees. Put it in your calculator, you get 1.39 times 10 to the 4th newtons. That's the force that's pulling it down the plane. So a truck on an incline has a greater force pulling it down than your automobile on that same inclined plane. That's why we get out of the way of trucks. A block weighing 10 newtons on a 30-degree ramp is being pulled upward at a constant velocity. If a 3 Newton frictional force acts down the ramp, what is the magnitude of F? So what I'm looking for is F. I must know everything else. So let's draw. And again, constant velocity tells me something. It tells me there's no acceleration. Now I have Fg acting down. What I'm really concerned with is Fd, which is the part of weight that's acting down the ramp. So I'm going to again say that my plane is positive. I'm going to say that's my x direction, and the sum of the forces in the x direction have to add up to 0. So now up the plane is positive. So F minus the force of friction minus the force down the plane have to equal 0. So when I rearrange my equation, since I'm trying to solve for F, I move it to the other side. I get the force is equal to the force of friction plus the force of down the plane. So 3 newtons, that's my force of friction that was given to you. The force down the plane is the weight of the box times the sine of 30 degrees. So 3 newtons plus 5 newtons equals 8 newtons.